So hello and welcome everyone. My name is Marcel Binz and I want to talk to you today about two projects that live somewhere on the intersection between cognitive science research and large language models. Probably I don't have to explain to you what large language models are, because if you don't know by now, you're probably living somewhere under the rock. But nevertheless, to give a short explanation, large language models are neural networks, often based on the transformer architecture, that are trained on vast amounts of data to predict the next word for a given text sequence. These large language models are perhaps right now the hottest topic in AI research. And to really demonstrate to you how hot of a topic they are, I brought the following figure with me, which shows Google Trend results for two search terms, for COVID-19, shown in red, and for ChatGPT, shown in blue. And what you can see in this figure is that by now, ChatGPT is the more popular search term on Google than COVID-19. Now, of course, part of this is because we as a society decided that the pandemic is over and that we are done with COVID. But I still think it demonstrates nicely that large language models permeate through all of our society and are already used by millions of people today. Now, while these models are only trained to predict the next word for a given text sequence, they have many interesting emergent abilities that go far beyond mere next word prediction. For example, they can be used to translate from one language to another. They can be used to write computer code that you can then execute, or they can solve challenging math problems. In the beginning of last year, we and also researchers from other labs found out that you can even place large language models into classical psychology experiments and get reasonable responses back. And I think this is quite the interesting observation, because it opens up totally new opportunities to analyze these models, which are often viewed as black box machines. Because now that means that you can essentially run classical psychology experiments on these models and analyze the resulting data in exactly the same way as psychologists have analyzed human data already for decades. Now, we did exactly this in a paper that is called Using Cognitive Psychology to Understand GPT-3, which is by now published in PNAS. In this paper, we looked at a particular large language model, in this case GPT-3, and tested it on a battery of classical psychology experiments. So I won't have the time to go over all of the results today, so I really present a subset of results that I find the most interesting. And one of the first things that we did was looking at a decision from descriptions paradigm, where a decision maker is presented with descriptions of two options and then has to state which of the two options it prefers. So, for example, a task in the setting could look as follows, where we say, imagine that we gave to you $2,000 right now to play a game, and then we ask the decision maker, which option do you prefer? There is either option F, which has 50% chance that you will lose $1,000, or there's option J, which has 100% chance that you will lose $500. And then the decision maker simply has to state whether it prefers option J or option F. And GPT-3 would do this by simply completing the prompt that is shown here with either option J or option F. So we tested GPT-3 on a large data set of such problems and first compared its performance to human performance. And the results of this analysis are shown in this plot here. The plot shows different models in the GPT-3 family that vary in the number of parameters that they have. These models range from the least complex model, the other model, to the most complex model, the Da Vinci model. And what we can see is that as the number of parameters increases, these models get better at the task. And the largest model from the GPT family, the Da Vinci model, even approaches human performance. Now, the model is still a bit behind human performance, but I'm sure if you would repeat this experiment today with the latest generation of large language models, you would find that these models would perform even better, maybe even outperforming human participants on this task. But What I think is, to me, more interesting in this case is the observation that both people and large language models are not perfect on this task, as indicated by the regret being larger than 0. And that means that these models must have some kind of biases. And in our analysis, we found that GPT-3, in fact, shares some of its biases with people. So, for example, it showed a framing effect, it showed a certainty effect, and it showed an overweighting bias. But on the other hand, there were also biases that are present in people that we did not find in GPT-3. Examples of this include a reflection effect, an isolation effect, and the sensitivity to magnitude perception. We also tested GPT-3 on another task, in this case, the horizon task, which is a two-armed bandit problem that is often used to detect different types of exploration behavior. In this task, a decision maker repeatedly interacts with 2 slot machines. The task begins with 4 forced choice trials, in which the decision maker is asked to pick or forced to pick a particular option, and then observes how rewarding that option is. And these 4 forced choice trials are then followed by either 1 or 6 free choice trials, in which the decision maker can choose freely which option to pick. Now, there are 2 conditions in the task. The first is an equal information condition, where the forced choice trials contain an equal amount of information for both of the options. So, for example, there could be 2 pieces of information for the red option and 2 pieces of information for the green option. And this condition is typically used to determine whether an agent applied a strategy known as random exploration, which is defined as picking the option with the lower expected mean value. And then there's a second condition, the unequal information condition, in which the forced choice trials contain an unequal amount of information for the 2 options. So in this case, for example, there could be 3 pieces of information for the red option and 1 piece of information for the green option, or the other way around. And this condition is used to detect directed exploration behavior, which is defined as picking the option that has been observed fewer times during the forced choice trials. So really trying to get at this fact whether an agent uses its choice behavior to reduce the uncertainty about a task. To test GPT-3 on this task, we first created a text-based version on it. In this text-based version, we first described the general setting, telling it that you are going to a casino that owns 2 slot machines and that you can earn money each time you play on one of these machines. We then provide a list of observations that have been observed so far. So, for example, saying that machine F delivered $51, machine J delivered $39, and so on. And then we ask the agent or tell the agent that it should try to maximize the sum of received dollars within a certain amount of additional rounds. And then we ask it which machine it wants to choose, and the agent has to pick either machine F or machine J by completing the prompt that is shown here. And after the decision, we provide feedback to the agent and append the list of previous choices that is shown here with the newly made observation. So we collected data from GPT-3 and compared it to human data. And the result of this analysis is shown on this plot here, where on the x-axis you have the trial index, while on the y-axis, or while the y-axis shows the regret. Again, lower regret indicates better performance. The regret of GPT-3 is shown in blue, and the regret of humans is shown in orange. And what we can see is that GPT-3 is better than people at this task, as indicated by its lower regret. However, while GPT-3 actually does quite well at this task, its behavior in it is actually quite different from how people approach it. And one difference you can directly observe from the plot on the left is that GPT-3 essentially shows no learning effects across trials, whereas people get better at the task as the more they interact with it. We also found that GPT-3, like people, sometimes picks the option with a lower mean value, so it really engages in random exploration, at least to some degree. But at the same time, we found that GPT-3 never picks the option that has been observed fewer times in the forced choice trials. So really, it does not engage in directed exploration, which is a type of exploration behavior that people quite frequently show. Now, in the paper, we looked at several other domains, the decision-making and exploration domains that I've just talked about, but also a deliberation setting for which we looked at a two-step task and a causal reasoning task. And we found that GPT-3 did well in many of these domains, including decision-making, exploration, and deliberation, but also that it failed at some of these domains, in this case, causal reasoning. So while GPT-3 overall did quite well, its behavior in some of these domains differed from human behavior. While it was reasonably similar to human behavior in the decision-making and deliberation settings, its behavior was vastly different from human behavior in the other two settings, in the exploration case that I've just presented and in the causal reasoning task. And this actually lets me nicely transition to the second project that I want to talk about today, in which we asked the question whether we can take a large language model and align it more with human behavior. Or in other words, can we turn a large language model into a model of human cognition? And to do so, we relied on the idea of fine-tuning. In this project, we first took data from different psychology experiments. In this example that I'm showing here, this is the Horizon task that I've talked about before. And then we created a text-based version of the task. We then passed the resulting prompts through the model and extracted its embeddings. And then we fine-tuned a linear layer on top of these embeddings to predict human choices. As a base model for our investigations, we relied on Llama, which is an open source large language model that was trained by Meta AI. And we then fine-tuned the final readout layer of Llama on data that comes from psychology experiments. We call the resulting model Centaur, in analogy to the musical creature that is half a human and half an ungulate. We then fine-tuned Centaur on two different domains. First domain that we looked at was decisions from description setting that we have seen before. And for this, we relied on the choices 13K dataset. So decision makers in these kind of tasks are provided with a text description for two options, and then they have to say which of the two options they prefer. And we measure the fit to human choices using cross-validated log likelihoods, and the plot shown here shows negative log likelihoods. So lower values indicate a better fit to human behavior. And what we can see is that Centaur is better than a random baseline and a Llama model without any fine-tuning, but also it is better than a traditional cognitive model, in this case, the BEAST model, the common model to explain human behavior in these kind of tasks. We then confirmed these results by looking at the second domain, a decision from description experience setting, for which we used the Horizon task data that I've talked about before. So in this setting, you have a decision maker that sequentially interacts with two slot machines with the goal of maximizing the total amount of accumulated rewards. And we again see that Centaur is better at explaining human choices than a random baseline, than a Llama model without fine-tuning, and then a traditional cognitive model, for which we used in this case the hybrid model, which contains a combination of different exploration strategies that are known to be used by people. So I think these results are already quite cool, but we really wanted to stress test this approach even more, and therefore we looked at whether it can also predict behavior on a task that was not seen during fine-tuning. So in this setting, we fine-tuned Centaur on the choices 13K dataset and the Horizon task data that I've shown before. And then we evaluated it on an entirely new task. And for the new task, we selected an experiment that was developed by Stefano Parmenteri's lab, which is essentially a mixture of a decision from descriptions and a decision from experience setting. So one option is provided through a list of previous observations, and the other option is provided in form of a description. In this setting, people tend to ignore the option that is provided via a list of observations and focus their decision-making processes on the option that is provided via a description. And we found in our analysis that Centaur also shows this behavior, while a standard llama model before any fine-tuning does not. And I think this is particularly impressive because Centaur was never fine-tuned on this task. It's only seen, it was only trained on data from the Choices 13K dataset and the Horizon task. So to summarize this, Centaur is a large language model that is fine-tuned on data from psychology experiments with the goal of aligning large language models more with human behavior. We have seen that Centaur is better at predicting human choices than traditional cognitive models, and that it in fact also captures human behavior on a task that was not seen during fine-tuning. So I think we really only scratch the surface of what you can do with this kind of approach in our current project, and there are many more interesting questions that only wait to be explored. One particular question that I'm really excited about is whether we can actually gain insights into human cognition by investigating the inner workings of these fine-tuned large language models. And I think, for example, you could apply methods from the explainable machine learning literature to these models and then try to infer how they solve the task. And maybe that can shed some insights into how people solve these kind of problems and to human cognition. So with that, I'm at the end of my talk. Thank you for your attention. And if there are any questions, I'm happy to answer them.